So we talked a bit about what polar graphs look like. It's worth looking at special cases that you can get from the conversion formula between polar coordinates and rectangular coordinates. Remember what the picture looks like if you want to do a conversion. The angle theta between, so here's the axes, and theta marks how far up you go and the distance r out. Could be in terms of the horizontal x and the vertical y, so that you've got four pieces of the right triangle labeled, useful for coming up with the conversion back and forth. In particular, what's highlighted on this slide is from the fact that cosine theta is the side adjacent over the hypotenuse, and the hypotenuse is r, and the side adjacent is x. So if cosine theta is x over r, x is r times the cosine of theta, and that's perfect for getting the x-coordinate out if you happen to know the polar coordinates of a point. Let's look at the particular polar equation, r cosine theta equals a. Well, that is just right for substituting what r cosine theta is as x. R cosine theta is x, and if x equals a, you know that is the equation for a vertical line. The vertical line is going to be relative to the y-axis, the vertical axis, to the right in the positive direction if a is positive, and a units, absolute a units to the left if a is negative. So either plus or minus from this vertical axis to get what the graph looks like if this is the polar equation. Let's try another one, this time for an equation that is going to simplify to a different Cartesian equation, r equals 4 cosine theta. The trick here is that r by itself doesn't have a particularly nice translation as Cartesian coordinates. I mean, you could do it with the Pythagorean thing and the square root of x squared plus y squared, but it would be much better if you do it in terms of something that doesn't have radicals in it. So the trick is to take this equation and multiply it left and right by r. So r times r on the left is r squared, and r times 4 cosine theta is 4r cosine theta on the right. Then r squared is x squared plus y squared, and 4 cosine theta times r is 4 times r cosine theta. And remember the translation that r cosine theta is simply the Cartesian coordinate x. So by multiplying both sides by r, we get an especially nice Cartesian equation. X squared plus y squared equals 4x. We can rewrite that equation to see what it gives by combining the x terms and the y terms. So let's move the 4x over and write x squared minus 4x plus y squared equals 0. And now x squared minus 4x has, that's two terms of a three-term, a perfect square trinomial. When you complete the square, the constant has to be 4. Half of the middle term coefficient, half of minus 4 is minus 2, squared is 4. So you put 4 and balance the equation by putting it on both sides, and that lets you write the equation as x minus 2 squared plus y squared equals 4. That looks like, let's go back, just look at it one more time. X minus 2 squared plus y squared equals 4. Think about the standard form for the equation of a circle. X minus h squared plus y minus k squared equals r squared. So we've got h is 2 and k There's no term with y there, so k is 0 and r squared is 4, so r is 2. That means that we're going to get out an equation of a circle whose center is at hk, that's at 2, 0, and where the radius is 2. So there's what it looks like. You can draw it in on this axis that has the spiderweb grid for polar coordinates kind of superimposed on a Cartesian grid to see center at 2, 0, and radius 2. Radius 2 units back, forward, up, and down to be what the circle looks like. And right center, right radius, that's what the circle is. It's in the polar grid. It's the same circle in the Cartesian plane. And it has an especially nice form in polar coordinates. So what's the general result? Let A be a positive real number. Then we're going to take r as 2a times the sine of theta as a circle. Radius a, center at 0a in rectangular coordinates. This comes from writing this equation as r squared is 2a r sine theta. That is x squared plus y squared is the r squared is 2a times r sine theta is y. So completing the square puts x squared plus y squared minus 2ay equals 0. And minus 2ay, it should be, to complete the square, it should be plus a squared plus a squared, and that's just right to be x squared plus y minus a squared equals a squared, center at 0a, and radius a. Much the same way, if it's minus 2a sine theta, that moves the circle to the left rather than to the right for the what it looks like on the plane. And if you, instead of using the sine function, you use the cosine function, 2a cosine theta moves the center of the circle in the x direction, since r cosine theta is x, and that moves the center to x equals a, 0. So it's going to go to, that'll be to the right, and minus a if it's negative to the left. Did I say it right? I hope I did. That if we've got sine, it moves it in the y direction. That's up or down. Cosine substitutes with the polar coordinates to the x direction, so that moves it left or right. Now let's look at a question about symmetry. What happens for a polar equation if you, instead of using theta, you use minus theta? So measuring the angle from the polar axis, that's the positive x-axis, this angle is theta, and this angle, if you measure in the opposite direction, is minus theta. So coordinates the same distance out would be to r theta, and that distance out r minus theta. So suppose you've got a polar function which has a symmetry about the polar axis. You'll be able to detect that symmetry by seeing whether, if you get the same polar function value going in a positive direction or a negative direction. And that is just right for the symmetry in the polar axis. So this is one of the first of several tests for symmetry we can talk about. Symmetry with respect to the polar axis is to consider what happens to a polar equation replacing theta by minus theta. If you get an equivalent equation. If the same points arise by plugging in theta as by plugging in minus theta, then the graph is symmetric with respect to the polar axis. And that symmetry shows up as a mirror image along that horizontal axis that is the pole. You look at the polar axis is out from the pole, and symmetry would be a point here, matching a point here, a wiggle here, looking like a wiggle here. That's the symmetry that the algebraic effect of replacing theta by minus theta, giving the same values out, shows. How about now if you want to think about replacing a different set of points? So what's happening here? This is the pole, and this would be the measure of the angle theta. But how about if we go out here and measure this angle? This angle is the angle that is, well, let's see, if this is 0, all the way around is pi, and pi, this is theta, so theta here makes this overall angle pi minus theta. 180 minus theta, it's the supplementary angle. So what would you see if you found symmetry about this kind of a line? Symmetry to the left and to the right of that line would be comparing, plugging in angle theta and plugging in the angle pi minus theta. So if you get the same values out by plugging in theta as pi minus theta, that shows a different kind of symmetry of the polar graph. That's symmetry with respect to the y-axis, and the y-axis is the line theta equals 90 degrees. That's pi over 2 radians. So you can check for that kind of symmetry by replacing theta by pi minus theta. If you get the same, get an equivalent equation out, then you can claim symmetry with respect to the line theta equals pi over 2. What we're doing here is going through symmetries that you are used to looking for in Cartesian coordinates and describing in terms of symmetry about the x-axis or the y-axis, and we just have to say what that means with points showing in the plane and denoted with this other system, using it with polar coordinates. There's another kind of symmetry that you might expect. That is symmetry with respect to the origin in Cartesian coordinates. And what does it look like here? Well, we don't have the quadrants quite illustrated in polar coordinates, but they're still there. This is quadrant 1, 2, quadrant 3. And if you've got a point in quadrant 1 reflected in a point in quadrant 3, that was symmetry of an odd function in Cartesian coordinates. How you describe that in polar coordinates? Well, a way of doing it is to say that you're going in for a given angle theta, you're going in a positive direction to get to the point in quadrant 1, and you're going in the negative direction to get to the point in quadrant 3. So this would be a way of describing it as substituting in different values of r. So if you use r or you use minus r, and either way you get a point that is on the graph of the polar function, then the polar function has symmetry with respect to the pole. Symmetry with respect to the pole is the symmetry with respect to the origin as we described it in Cartesian coordinates. So symmetry with respect to the pole happens as a criterion, as a check for that. See what if you replace r by minus r. If you get an equivalent equation out, then you've got symmetry with respect to the pole. So these versions of symmetry that arise are analogs of what happens for Cartesian equations, and they're useful in the same way. You can check and save yourself some time, or double check to make sure that you are plotting appropriate points to when you use these tests for symmetry for the polar equations. In the lab, and if you play around with the polar grapher that I wrote for the course, see that these tests for symmetry match algebraically what you see when you plot some of these polar equations.